First of all, I would like to thank for organizers for giving me this chance to speak in the ICM Satellite Conference, and moreover, the chance to come again in Korea. Okay, so I'm going to talk about the complexity 1 GKM graph with the symmetries and obstruction to be a torus graph. So in this talk, the main object of this talk is a GKM graph. So the first, I will briefly introduce the GKM theory. Maybe some of you know about that, but I will recall it again. And next, I will define the GKM graph abstractly. And in the next sections, I will introduce the problem in this talk. So this problem is a kind of the extension problem of the GKM graph. And to solve it, I will introduce some obstructions. So I will introduce obstruction in this section too. And in the final section, I will apply these obstructions to the complexity 1 GKM graphs with symmetries. Okay, let's start the first section. This is an theory of GKM theory. And we would like to think about GKM graphs in this talk. And the motivation of the GKM graph is an GKM manifold. And this GKM manifold is defined by Guillemin-Zara in 2000. The definition is as follows. Let M be an even-dimensional manifold, and there is a torus action, n-dimensional torus actions. If this torus action satisfies these blue line conditions, then we call it a GKM manifold. So that is to say, there is a fixed point, and the dimension of M sub 1 is equal to 2. This M sub 1 is called one skeleton of this manifold. The one skeleton means the elements, the set of the elements whose orbit dimension is less than or equal to 1. Okay, so such kind of sets is a dimension equal to 2. Then we call it a GKM manifold. In other words, this is the same with the structure, the condition that M1 over T is on the graph, has a structure of the graph. And GKM theory is briefly is something like this. In the geometric side, there is a GKM manifold. And we can define the graph from this one skeleton over T. Then we can get the GKM graph by using the tangential representation. And a tangential representation is the representation around the fixed point, the Tn representation around the fixed point on the tangent space. Then we get some of the representations. And this representation give a labeled graph. This representation attaches on each edges of the GKM graph. Then we get a labeled graph. And this labeled graph is called a GKM graph. And GKM theory tells us that this geometry of the GKM manifolds can be studied by using the combinatoric structure of the GKM graphs. And on the other hand, the geometric structure of the GKM manifold tells us the combinatoric structure of the GKM graphs. This kind of relation is called GKM theories. And let's look at some examples. The GKM theory is maybe regarded as a generalization of the toric geometry. So GKM manifold contains toric manifolds. Okay? And more generally, torus manifold, GKM manifolds contains a torus manifold, which is introduced in a previous talk by the Anton. And the particular example is a 2n dimensional sphere. The higher dimensional 2n dimensional sphere is not a toric manifold. So this contains a more general class of the manifolds. And moreover, this is an interesting class of the GKM manifold, a homogeneous space with the same rank. With the same rank means that this G and H are compact connected group. This has an Tn as its maximal torus subgroup. Okay? And then this Tn acts on G over H, and this satisfies these conditions. This is an GKM theory. And in this theory, I would like to think about this problem. So let M2n Tn be a GKM manifold. Then when this GKM manifold extends to more general TL actions, or compact connected group G, whose maximal torus is Tn. Okay? I'd like to think about this kind of problem by using the GKM theory from the combinatorial point of view. So I will introduce a GKM graph abstractly. Now, usually GKM graph is defined by using the GKM manifold, but we can also define it abstractly, so without geometry. So I will define it without geometry. Okay. So let gamma this is an abstract graph. That is, this is a set of the vertices and edges. Be an M-variant graph. So M-variant means that all of the outgoing edges for each vertices whose cardinality is exactly M. So, for example, these three graphs are M-variant graph. So, left two graph is an three-variant graph because each vertices has exactly three outgoing edges. Okay, around this there is three outgoing edges. Here, all of them has three outgoing edges. And the right example, this is a four-variant graph because each vertices has four outgoing edges. Maybe you can easily check it. I only think these kind of graphs in this talk. And the definition of the GKM graph, sometimes I put on complex. GKM graph is a labeled graph, gamma A. And this label, so this A represents the label. And this label is attached on the edges, each edges. So this label this is defined some function from the edges to some vector space, C to the N. So sometimes we will identify it in the secondary cohomology of the classifying space. And this N is ranging this range. And this function, actually this label satisfies the following three conditions. Then we call this gamma A, this pair gamma A GKM graph. Okay, let's recall the functions. This function is often called the axial functions. And the axial function satisfies the following three conditions. The first condition is let PQ be an edge, some edge. And now we regard this E gamma as an oriented edge. So we distinct PQ and QP. Then there are two levels, APQ and AQP. Then this APQ and AQP satisfies this condition. This is the first condition. So it means that if you attach PQ, if you attach alpha on the PQ, then the level on the QP must be minus alpha. Okay? Alpha is an element of the H2 BTN. And the second condition is the following conditions. Now, as I said before, this is an M-variant graph. So there exists an M outgoing edges from the each vertex is P. And let's take a set of the axial functions around these M vertices. Then this gives an M vectors. And M vectors satisfies pairwise linearly independent. So it means that if you take two elements from here, then they are linearly independent. So let's look at the example. The left one is an alpha, beta, gamma. So this is a set of the axial functions and P. Alpha, beta, gamma is the generator of the secondary cohomology of the BT3. Then this is automatically linearly independent. So it is a pairwise linearly independent automatically. And the right-hand side, the example of the right-hand side is not linearly independent. But it's a pairwise linearly independent. Because if you take two elements, for any two elements, they are linearly independent. Okay? And these are first two conditions. And the third condition is a little bit complicated conditions. So I will explain by the blackboard. So this condition says that for any PQ is an edge. So this is an edge, this is an edge, some edge. Then there exists exactly M outgoing edges from P and from Q. Okay? And then there is a bijection from the EP gamma to the EQ gamma. Okay? So we will denote it as nabla PQ. And which satisfies these blue line conditions. So it means that if we say this is an E, then there is a corresponding edge here, nabla PQE. And we will attach a label on this edge, AE, and on this edge, A, nabla PQE. Then this blue line says that there is some integer, CPQE. This is an integer. And the differences of these two levels satisfies is denoted by this integer CPQE and a level attached on this APQ. Now this is inside the integer and this is inside the C to the N. Okay? So this is the third conditions. And if there is this kind of bijective map, then this bijective map is called connections. And if these three conditions satisfied, then we call gamma A a GKM graph. So let's look at an example, a concrete example. For example, these two graphs with level graphs are GKM graphs. So let's check it. For example, in the left example, this is like this one and this one, PQ. This is the left example. And the next example satisfies this. We attach this part is alpha, and then this part is minus alpha. So this satisfies the first conditions, and also this satisfies the first condition. If we put this is minus alpha minus beta, then this part is alpha plus beta, and this is beta. Then this part is minus beta. So it satisfies the first conditions. Okay, and the second condition was pairwise linear independence. So each EP and EQ. It satisfies pairwise linear independent, because if we take two elements from here, then it's a linearly independent. This EQ, for this EQ, this also satisfies. So it satisfies pairwise linear independent. And moreover, this satisfies the third conditions. So let's check it for the E1 to E3. Now for the E1, now let's think about these directions. Then this edge, so along this E1, this edge corresponds to this edge. Okay? So on a nabla E1, this E1 corresponds to the different direction of the E1. And it satisfies these conditions because it's a corresponding edge, a corresponding level is minus alpha, and the original level is alpha. So minus alpha satisfies this is exactly minus 2 alpha. And alpha is a level on this edge. So in this case, this CE1, E1 is exactly minus 2. Okay? And now nabla E1 along this edge, this E2 corresponds to these directions. Because otherwise, we put this direction, then this condition doesn't satisfy. So E2 goes to E3 bar. E3 bar means that this direction. This corresponds to this direction because this satisfies this equation. Now minus beta minus alpha minus beta. Minus beta is here, and minus alpha minus beta, whose difference is exactly 1 times alpha. So the integer E1, E2 is equal to 1. Okay? And similarly, in this part, we can check this kind of things. E3 corresponds to E2 bar. And in this case, it's a constant is the corresponding element is alpha plus beta. So alpha plus beta minus beta is equal to 1 times alpha. So this is CE1, E3. So there is these kind of constants. And for other edges, this also satisfies. So this left-hand side graph is on the GKM graph. And actually, this constant is very important to define the obstructions. So I will compute it carefully in this case. Okay. So let's return to the program. So in this talk, I would like to think about the following kind of programs. So let gamma A be an invariant GKM graph. Then the problem is, so actually this is a combinatorial interpretation of the problem of the when this Tn action extends to TL actions. Okay? So this is a combinatorial interpretation is as follows. When does this actual functions, actually this is called an Mn type actual function. M means an invariant graph, and N means a target space of these actual functions. When this Mn type GKM graph extends to ML type GKM graph, and this L is a more general number of the N. So I would like to solve this kind of problem. So let me show you the examples. In this case, this left-hand side is a 3-2 type GKM graph. Okay? And on the other hand, this is a 3-3 type GKM graph. So if we put gamma, if we put alpha plus beta to the gamma in this 3-3 type GKM graph, then we get this GKM graph. Okay? So it means that this 3-2 type GKM graph is extended to this 3-3 type GKM graph. Okay, I would like to study this kind of things. So when this usually MN type GKM graph extend to ML type GKM graph. So let me define the obstructions. To define the obstruction, I will show you the key fact. So what kind of things is invariant under the extensions? So if there is an extension gamma A tilde, or ML type extension of the gamma A tilde of MN type GKM graph, then the key fact, this is also noticed by Takuma in 2004, the integer I computed here, this doesn't exchange under the extensions. So it means that this gamma A and gamma A tilde are GKM graph. So by the third conditions, there exists this kind of equations. And because this is an extension, so there is an projections onto the gamma A. So under these projections, this integer doesn't change. So actually, this is a very important fact. So these are invariant. So these kind of coefficients are invariant. So it means that we can define this map from the edges to the t to the m by using these coefficients, these integers. And actually, this map is invariant under the extensions. Okay. So let me compute some of the brief examples. Actually, this example is this example, and we've already computed this C gamma A on this line. Because in this case, we will attach the order like here 1, 2, 3, and here is also 1, 2, 3. Then for the C gamma A, C gamma A, E1 is defined by the previously. This is just an CE1, E1, CE1, E2, and CE1, E3, like this. And in this case, we've already computed these integers. Here, CE1, E1 is a -2, and CE1, E2 is 1, and CE1, E3 is 1. Okay. So we have this part, okay? This part. And similarly, we can also compute other C gamma, other these functions. So this direction, C gamma A E2 is 1 minus 2, 1, and C gamma A E3 is 1, 1 minus 2, and is another direction, C gamma A E1 bar is -2, 1, 1, and E2 bar is 1, -2, 1, and E3 bar is 1, 1, -2. Okay. And okay, let's define the obstructions. Now, obstruction. The idea to define the obstruction is the modified of the definition of the equivalent cohomology of the GKM graph. Actually, this is defined by Brady and McPherson's. Actually, I will omit details about this, but by using their ideas, then we can define the T module as follows from the C gamma A. Okay, let me explain that. This G module is attaching some of the vectors on each vertices. So for example, let FP here, FQ here, and this FP, FQ is some vectors in C to the M. And this M is the number of the edges, outgoing edges. And now there is some isomorphism which is induced from the connections. And then we can compute this value. Now FP is moving by nabla PQ to this T to the M. Then we may compute. We may take these differences like this. Then these differences is exactly written by FQ, QP, and this previous function C gamma A QP. Now this FQ QP is some integers. Now FQ may be regarded as C to CM, and this C to CM is assigned to each integers. For example, here is FQ, say E1, then FQ E1, and here is FQ E2, something like this. Then we will attach here FQ QP, and FQ is in this case is FQ E1, FQ E2, and FQ QP, like this. And we will put this integer here, and C gamma A QP is inside C to the M. Okay. I will take this kind of module. Then this gives an obstructions. Okay. So this is a theorem, one of the main theorem of this talk. Now this Z module is actually it's a free Z module, and with whose rank is in this range from N to the M. And if there is an ML type extensions, and now we assume this gamma A is an ML type GKM graph, and if and only if this rank of the O C gamma A is greater than or equal to L. So it means that if this rank is N, then there is no extensions. Okay, so this gives an obstruction from this theorem. So let's briefly compute in this case. Now we've already get C gamma A in this case like this. But then we can compute the OC gamma A in this case like this. So maybe I have time to compute it. Now OC gamma A is an vectors which are assigned on each vertices. So first we assume this part is x, y, z. X corresponds to the first edge, and y corresponds to the second edge, and z corresponds to the third edge. And this is x prime, y prime, z prime. Then this says that now there is an okay. Let's compute along this edge. Now nabla E1 gives an this edge to this edge, and this second edge to the third edge, and this third edge to the second edge. So this is just 1, 0, 0, 0, 1, 0, 0, no. 0, 1, and 1, 0. Okay? So this 0, 0, 1, 0, 1, 0 differences is written by, in this case, now if QE1 bar is this range, these directions, and this direction corresponds to x prime, is x prime times, and now it's C gamma A is minus 2, 1, 1. So by computing this, then we get, so I have no time, so we can easily to get this x prime, y prime, z prime must be minus x, minus y, minus z. And moreover, we also have x plus y plus z equals 0 by using this kind of computations. Okay. So we see that in this case, this free module is an rank 2. Okay. Oh, I'm sorry. This is rank 2. So it means that this is rank 2, so it's less than 3. It's not 3. So this is no, there is no 3 type extensions in this case. Okay. So this is also proved by using the Shinichi Takuma's obstruction, which is introduced in 2004. In his case, he uses a holonomy on a GKM manifold. But in this case, we use the idea of the Pradhan-MacPherson. So these are different type of the obstructions. Okay. So let's apply this obstruction to the complexity 1 case. So what is a complexity 1 GKM manifold? So let gamma A be an MN type GKM graph. Of course, M is greater than or equal to N. Then if we call this is a torus graph, if M equal N, okay? This is a maximal extreme case. And if M equal N plus 1, then this GKM graph is called a complexity 1 GKM graph. Okay? And I want to think about the following problem. Actually, this is my motivation to construct this kind of obstructions. When this complexity 1, actually this is GKM manifold, extends the complexity 0 GKM manifold. This is called a torus manifold, okay? Which is introduced by Anton previously. And actually, complexity 1 GKM manifold, which is corresponding to the complexity 1 GKM graph, is a very wide class. So I will assume the following conditions. Assume that this complexity 1 GKM graph have a rank 2 or 3 Y group actions. So it means that it's a symmetric group or signed symmetric group or dihedral group, only in this case. Actually, this is a motivation. There is a motivation on these assumptions. So let M2 and Tn be an GKM manifold with an almost complex structure. Then actually, this is a fact. If this GKM manifold extends to the G actions, okay, more general compact connected D group actions, then its Y group acts on the GKM graph induced from this GKM manifold. Okay, this is the fact. So I will assume there is symmetries on the GKM graph. And I also have these propositions. Actually, this proposition is known from the Boyd-Shintaro classification result of the maximal compact subgroups, maximal rank compact subgroups. Okay. So let M2 and Tn extends to the MG, and moreover, this G action is untransitively. Then this N must be 2 or 3. Okay. So it means that the dimension of the GKM manifold is an 6 or 8. Okay. And if this dimension is 6, then there exists just the following 4 cases. That is, this is a Frag manifold, or a complex quadratic, or a complex projective space, or a 6-dimensional sphere. Actually, this is well known that there is an almost complex structures on the 6-dimensional sphere. Okay, and in a 8-dimensional case, in this case, this is just an complex Grassmannian. Okay, a 4-dimensional, 2 planes in the 4-dimensional complex space. Okay.
And what is your H here?
H. In this case, I'm sorry. In which case?
H and G quotient H.
Quotient H. This means that G acts on M transitively, and it's a isotropy subgroup. So.
Free action. H acts freely on G.
No.
It's the same rank.
Right. That's right. Okay. Okay. So this is a final main theorem in this talk. So this is first part is classifications. So if gamma A be is an 3 or 4 variant complexity 1 GKM graph with the previous symmetries, rank 2 or 3 while group symmetries, then this gamma A must be one of the following graphs, GKM graphs. Actually, this is a classification. This is there is no relation with the previous obstructions. So by using this classification, we know that there is just this 8 type of the GKM graph. Actually, the actual function is very small, but anyway, the first part is first graph is actually this graph, and the second graph is this kind of graph. But these two graphs look same, but their actual functions are different, and also this kind of graph. And these two graphs are combinatorially same, but their actual function is different. And our 4 variant case is just these 2 cases. Okay, I will get this kind of classifications. And furthermore, by using the previous obstructions, we get that this gamma A extends to the torus graph. Okay, so it means that 3-3 type GKM graph or 4-4 type GKM graph. If and only if this second graph or third or fourth graph or 7th graph. Okay, otherwise they are not extend to the torus graph. And actually, there is some geometric models in each cases. So let's look at that in the final sheet. So this first one is corresponding to S6. Okay, S6. And as you know, S6 is not a toric manifold. Okay, so there is no extension in this case. And the second one is CP3, and the third one, CP3 sharp CP3, is a connected sum. And the fourth one is this kind of fiber bundle. This is a CP1 bundle over CP2. All of them is a toric manifold. Okay, so I'm sorry. Okay, and these are corresponding to these 3 graphs, and these 3 graphs are coming from the toric manifold. And the fifth one is a Frag manifold, corresponding to Frag manifold. So Frag manifold is not the toric manifold, so it's not, there is no extensions. And this 6th one is these are the same combinatory structures, but this is coming from the complex quadratic. It's called the Q3. Q3 is, as is well known, this is not a toric manifold. So this is not coming from the toric manifold. And this seventh graph is on a CP4, graph of CP4. So it extends to the toric manifold. And the eighth one is coming from the Grassmann manifold. And Grassmann manifold is not a toric manifold. So this is also corresponds to some of the geometric interpretation, geometric sense. Okay. Okay. I'll stop here. Thank you for your attention.